In this video, we're going to introduce the concept of a function. Functions are fundamental to college algebra, and we pretty much spend the entire semester discussing different kinds of functions. So let's start by defining a relation. The root of the word relation is relate. So fundamentally, we're talking about how multiple things are related to one another. So specifically, a relation tells you how two quantities are related. In other words, how you take an input and get an output from it. So we often express relations as sets of ordered pairs of the form x comma y. So each x is considered an input, and then the y that goes with it is considered the matching output. So when we're talking about a relation, we're talking about multiple ordered pairs of this form. So the set of all x values, otherwise known as inputs, is called the domain. And then the set of all y values, our outputs, constitute the range. So again, when we're talking about a relation, it's a big set of inputs, a big set of outputs, and then the combination that relates the inputs to the outputs. So that's what we define as a relation. Now let's talk about functions. A function is a relation in which each input, in other words, each x, is matched to exactly one output y. In other words, there are no repeated x values in the ordered pairs. Once an x is matched to a y, that's the only y it's matched to. So the reason we care about functions is because for everything we put in, we know exactly how to determine what we're going to get out. For anything we put in, there is only one output. So it's a well-defined relationship where inputs match exactly to outputs, and there's no confusion about how two numbers are related. One thing to keep in mind with functions is that y values can be repeated. In other words, if we have two different inputs that match to the same output, that's okay. As a matter of fact, all of our inputs could match to the exact same output and it might still be considered a function. We just have to make sure for each input it is uniquely matched to an output. In other words, we can't put an input in and then have some confusion about which output we're supposed to match to. So let's look at a couple examples of relations expressed as ordered pairs. So we want to determine whether each relation is a function, and then we want to find the domain and range of each. So our first relation has the ordered pairs 1, 3, 2, 3, and 3, 5. So first thing we want to decide is this relation a function? The way I determine this is by looking at the x values in each of the ordered pairs. So in this case, this relation only has 3 ordered pairs, and the x values are 1, 2, and 3. Because of this, because each x value is unique, it's matched individually to a single output. So 1 matches to a single output, 2 matches to a single output, and 3 matches to a single output. So in this case, this is a function. There are no repeated x values. One thing to notice is that with the first 2 ordered pairs, there is a repeated y value. So 1 matches to 3 and 2 matches to 3. That's not a problem. We can match different inputs to the same output. However, we know that for each time we put in 1, we're going to get out a 3. For each time we put in 2, we're going to get out a 3. There's no confusion about if we put in 1, it could go to 2 different outputs. That's what we mean by a function versus a relation. So in this case, this is a function. The domain is going to be the set of all x values, and the range is going to be the set of all y values. So our domain is 1, 2, and 3. Our range is 3 and 5. Now notice with the range that we have 3 ordered pairs, we have a repeated output of 3. When we write the range in set notation, we only write the 3 one time. That's one thing that's special about set notation is you don't repeat values. So even if that value occurs more than once in whatever situation we're talking about, we only write it once in the set notation. Let's look at another one. So now we've got 3 ordered pairs. We've got 2, 3, 2, 4, and 3, 5. So first thing we want to decide is this a function? I have to base it on what my x values are. So in my relation, I have 2, 3, 2, 4, and 3, 5. Well, those first 2 ordered pairs may be a problem. I've got an input of 2 and it matches to 3. And then I also have an input of 2 that matches to 4. So this is not a function because the input x equals 2 is repeated. If I wanted to determine what is my output based on an input of 2, I'd have to have more information than just the input because I know based on this relation that that input of 2 could match to 2 different outputs. So that's why this is not a function, because without extra information, we can't determine what the output is that matches with an input of 2. However, this is a relation, so we can still talk about domain and range. Domain is the set of all x values. Range is the set of all y values. Because there's a repeat in the domain, we only write the repeated value once. Anything that can be written in terms of ordered pairs can also be used to generate a graph. So now we're going to consider what happens when we have a relation or a function represented by a graph. So when a relation is represented by a graph, we use what we call the vertical line test to determine if the relation is a function. So the vertical line test states if any vertical line, keyword any vertical line, crosses the graph more than once, then the relation isn't a function. Now, conceptually, if you picture what a graph looks like, there's no way we can draw every single possible vertical line. So it's really just a visual element. So if you can find any vertical line that crosses the graph more than once, in other words, 2 or more points, then the relation is not a function. And then if a relation is given as a graph, the domain and range are typically written in interval notation. Usually we can't just make a list of inputs and outputs because we have continuous pieces of our graph. In other words, we have infinitely many elements in the domain and range. So interval notation is a convenient way of expressing a situation where there are many things that we couldn't list out. So let's look at an example. We want to determine whether the graph represents a function, and then we want to find the domain and range. So here's our graph. We've got a circle, and it's centered at the point 0, -3. So first thing we want to decide is, does it represent a function? Well, if we can draw any vertical line anywhere on the graph that crosses the graph more than once, then it's not a function. Well, this is pretty clear that we can draw a vertical line pretty much anywhere on this graph, and it will cross the graph more than once. So it fails the vertical line test, and it's not a function. Now let's talk about domain and range. So domain represents x values, range represents y values. So the easiest way to consider domain and range when you have a graph is, imagine if you were to take the graph and project it onto an axis. So say you were to take this graph and squish the graph onto the x-axis, onto the axis that represents the domain. So imagine taking that circle and then squishing every point on the circle so that it lies on the x-axis. What values would it cover? Well, it would cover everything in that shaded area. Anything outside that area is not on the graph. So all the points in that shaded area represent our domain for our function. So in this case, the domain is everything from -3 on the left-hand side to +3 on the right-hand side. Anything less than -3 or anything greater than +3 is not part of the graph. So that's going to be our domain. We're going to do a similar thing for the range. Range is represented by y. So now do the same thing, but imagine projecting or squishing the graph onto the y-axis. So all the points to the left are squished onto the axis, all the points to the right are squished onto the axis, and we fall under that particular shaded region. So our range is going to be everything from -6 on the bottom up to 0 on the top. And then anything less than -6 or anything greater than 0 is not included in our range. Let's look at another example. So same thing, we want to determine whether this graph represents a function, and we want to find the domain and range. So here's our new graph. One thing I want you to pay attention to is the hole at the bottom of the graph. Down there at what we can think of as kind of the vertex on the graph, there is a hole. So we're going to have to take that into account when we start to consider domain and range. But first, let's decide if it's a function. So imagine putting a vertical line anywhere on this graph. Is the vertical line going to cross the graph more than once? It's pretty clear from this graph that there aren't any spots where anything would cross multiple times, so this is a function. It does pass the vertical line test. Now let's look at domain and range. So remember, domain is represented by all the x values. Range is represented by all the y values. So for domain, imagine sliding all the points on this graph onto the x-axis. We also have to slide that hole at the bottom of the graph. So when that hole slides up onto the x-axis, there is a hole on the x-axis. So everything to the left of that hole and everything to the right of that hole is solid and continuous. It continues forever and ever in either direction, but that hole slides up there. So that means there's going to be a break somewhere in the middle of the domain. So if we're talking about domain, we're talking about x. So the break is at x equals 0. So we have all the x values from -infinity to 0, and then we have all the x values from 0 to infinity. We just don't have 0 itself. So the way we write this is as two intervals, everything from negative infinity to 0, not including 0, because 0 is a break in the graph, and then everything from 0 to infinity, but again, not including 0. Because these are two separate intervals, we combine them with the union symbol in the middle. Now let's look at the range. So for the range, we're projecting onto the y-axis. So take everything from the left side of the y-axis, everything from the right side, and all those points are slid onto the y-axis. So here we still have to consider that hole, but we kind of lucked out because the hole was already on the y-axis. So there is a hole on the y-axis. There isn't anything below the hole, but everything above the hole is included. So the hole starts at -4, and then we have everything above that. So the range is -4 to infinity, but not including -4, because that's where the hole in our graph is. So we can represent functions in terms of ordered pairs. We can translate those ordered pairs into graphs, but in algebra, our preferred representation for a function is equation form. Now things get a little more complicated when we put things in equation form. We don't have a nice pretty formula to determine whether or not an equation represents a function. And it's also hard to find the range, it turns out. So the only thing we're going to focus on for things in equation form is what the domain is. So to find the domain for an equation, we're going to start with all real numbers. In other words, assume we can plug in anything we want to the equation, and then consider excluded x values. So the reason we do this is because there's only a handful of things we have to exclude. In most cases, we can apply the operations in an equation to any number we want and everything is completely fine. The only situations where we run into a problem are situations where an x value gives a divide by 0 error. In other words, it makes the denominator 0. The only time we have to worry about something like that is if the equation we're given has a denominator and there's a way we could actually generate a 0 in the denominator. So if our equation has a denominator, we have to take into account that certain things might make the denominator 0, which we know is illegal in algebra. The other situation we have to take into account is anything that gives a negative inside of an even root. In other words, a square root, a fourth root, a sixth root, etc. So we cannot take a square root of a negative number. That's not defined as something on our number line or something that exists in the coordinate plane. So whenever we have any type of square root or fourth root or sixth root, most commonly just a square root, we have to make sure that everything we plug in is going to make the number under the square root greater than or equal to 0. Any x value we could plug in that would give us a negative number under the square root has to be excluded from the domain because it gives us something that's not okay. It gives us something that's not defined. So let's look at a few examples where we have a function in equation form and we want to determine its domain. So we're going to just assume what we're given is a function. We're kind of sweeping things under the rug, but for our purposes, all we really care about right now is finding the domain for whatever equation we're given. So here's our first two equations. Notice these are rational equations. They have a numerator and a denominator. So what we have to take into account here is that because each function has a denominator, we have to make sure the denominator is not 0. So what we do in this case is we set the denominator equal to 0 and we solve that equation in order to determine which x values are excluded. Any value of x that we could plug into the denominator that would make the denominator 0 is not part of the domain. Anytime the denominator is 0, the entire expression is undefined. It's just something we're not allowed to do in algebra. So for each of these, we're going to set our denominator equal to 0. For my first one, my denominator is x squared minus 4. So I'm going to forget about the numerator for a minute, but I'm just going to take that denominator and set it equal to 0. So now I have a quadratic equation that I want to solve. I can go about solving something like this in a couple different ways. Maybe I can factor it. However, in something this simple, because it's just x squared minus 4, there's only one x in the problem, so let's just move the 4 over. So now we know x squared is equal to 4 and we want to solve for x. So now we want to take the square root of both sides of the equation. One thing you have to keep in mind when you're solving an equation like this, if you apply a square root to the problem, you have to put a plus minus on one side of the equation. The reason you have to do this is because if you were to start with that last step at x equals positive or minus 2, if you were to go backwards, then both plus or minus 2 would solve the previous step. So at x squared equals 4, you could plug in a positive 2 or a negative 2, and both would give you a correct solution to that particular equation. So when you're starting with something and taking a square root in an equation, one side has to have a plus or minus tacked on. So in this case, both positive 2 and negative 2, if plugged into that particular equation, would make the denominator 0. So those are the two values we're going to exclude from the domain. So the way we write the domain is we take all real numbers and we split it up around these two numbers we're excluding. So we can have any number we want as long as it's not negative 2 or positive 2. So if you visualize what this looks like, it's everything less than negative 2, everything between negative 2 and 2, and then everything greater than positive 2. So that's actually three separate intervals. It's negative infinity to negative 2, not included negative 2, so we put parentheses. Then everything from negative 2 to 2, so everything between the two excluded values, again with parentheses because we're not including those endpoints. And then everything from 2 to infinity, but not including 2. So if we have two excluded values, it actually splits all real numbers up into three parts. So in this case, we use two union symbols to combine these three intervals. Let's look at the next one. So y is equal to x minus 3 over x squared plus 4. So now I set x squared plus 4 equal to 0. Let's see if we can solve this the same way. So move the 4 over, we get x squared equals negative 4. There's a problem here though. If we try to take the square root of both sides, the right-hand side becomes the square root of negative 4, which is undefined. At least for our purposes, it's undefined. It's not a real number. It doesn't exist anywhere on our coordinate plane. Because there is no solution to this particular equation, there are no exclusions from the domain. In other words, we can plug in anything we want, and we're not going to divide by 0. So in this case, the domain is all real numbers. One thing I want you to notice is that we didn't do anything with the numerator. The numerator can be whatever it needs to be. The numerator can be 0, it can be positive, it can be negative. It doesn't have any impact on the problem. So even if the numerator is 0, in this case for either of these, if we were to plug in x equals 3, the numerator would be 0. That is completely okay. 0 divided by anything else is still just 0. That's okay. It's just anything divided by 0 that becomes a problem. So when we're talking about domain, we don't consider what happens in the numerator. All we have to worry about is what happens in the denominator. Let's look at a couple more equations. So again, we want to find the domain, and we're just assuming what we're given is a function. So here we have square roots. One is just a square root by itself, and one is a square root in a denominator. So let's see what happens with these. So the problem is each function, again, has a square root, and a square root cannot contain negative values. The second function is actually a special case because there's a square root and it's also in the denominator. So we can't have a negative in the square root, and the denominator can't be 0. So we're going to have to deal with two components there. So we're going to deal with this one slightly differently than the one we did before. We can't really figure out individual excluded values because there's an infinite number of excluded values. Half of the number line is going to give us things that are a problem under the square root, and then half of it is going to give us things that are okay under the square root. So the easiest way to address this is just to take what's under the square root, what we call the radicand, and just set it to be greater than or equal to 0. In other words, we're finding things that are included. As long as x plus 9, or whatever happens to be under the square root, is greater than or equal to 0, then we're okay. So essentially what we're doing is we're finding the domain itself as opposed to finding things that are excluded from the domain. So let's see what this looks like. So square root of x plus 9, we know that x plus 9 cannot be negative. So x plus 9 has to be greater than or equal to 0 in order for this square root expression to be defined. So I want to determine what x has to be to make this inequality true. So I can subtract 9 from both sides, and I get x has to be greater than or equal to negative 9. So this is actually the domain. It might help to think about what values are included in this particular inequality and what values aren't. So if you imagine plugging in negative 9 to this function. So we plug in negative 9, we get negative 9 plus 9, which is 0. The square root of 0 is 0. Now imagine plugging in something greater than negative 9. So say we plug in negative 8. So negative 8 plus 9 would be positive 1. Square root of positive 1 is 1, so we're okay. We're at something that's defined. Anything greater than negative 9, same situation. You may not end up with a pretty square root, but at least you'll end up with something that you can take the square root of. Now, what if we go in the opposite direction? So what if we plugged in a negative 10? So negative 10 plus 9 would be negative 1. Square root of negative 1 is not defined for our purposes. It doesn't exist anywhere on our coordinate plane. So anything less than negative 9 becomes a problem. So x greater than or equal to negative 9 is defined as our domain for this function. So everything from negative 9 to infinity, notice in this case we're including negative 9, so we put a bracket around it. If we plug in negative 9, as we just previously determined, it gives us a 0. We can take the square root of 0, that's completely fine. So our domain is everything from negative 9 to infinity. Let's look at the other one. So now it's the same square root, but the square root is in the denominator. So we're just going to tweak this one tiny bit. So now x plus 9 has to be greater than or equal to 0, just like it was before. It's the same square root as before. However, if it's equal to 0, that's when we're dividing by 0, which we know is also a problem. So the way I fix this is by writing the inequality x plus 9 is strictly greater than 0. So again, if it's equal to 0, we're dividing by 0. As long as we're strictly greater than 0, then we're fine. The square root is defined and we don't have an issue with the denominator. Other than that, we treat it the same way. So subtract the 9, we get x is greater than, strictly greater than, negative 9. So the domain is almost the same, except we're not including negative 9 because that's the number that would make us divide by 0. So now that we've talked about what a function is, what domain and range are, how to determine whether something is a function, how to find domain and range, potentially depending on the situation, let's introduce a new notation for functions. So this is just a new way of writing what we already know, what we've already seen, so that we communicate a little bit more information about our situation. So this is the particular notation we're going to carry throughout the course. So when a function is defined by an equation specifically, we can rewrite it in what we call function notation. So say we have a really basic function. This is actually a linear function, y equals x plus 2. So again, x is our input, y is our output. We're going to rewrite it in this form with this f and this x notation. So let's break this down a little bit. So the left-hand side of the equation, the new version anyway, is read as f of x. So normally when you see parentheses, parentheses mean multiplication. This actually doesn't mean multiplication. This means we're plugging something in. So if you have any experience with programming or computer science, you've probably seen this notation before. You have a function name and then you have parentheses with some number plugged in. This is what we have here. So f is what we're thinking of as the function name. So we're giving a name to the function. So if I'm referring to function f and you're referring to function f, we know we're referring to the same thing. So f is just a label for the function. The x in parentheses represents the function input, and it can be replaced by a number. So if we want to find what the output is for a particular input, we put in that input there to show that that's the particular input we're considering at the moment. X plus 2, the right-hand side of the equation, is the rule that takes an input and gives the matching output from it. So for whatever we choose to put in the parentheses in place of x, we can also plug that into the other side of the equation in place of x, and we apply the rule, whatever algebraic operations are there, in order to figure out what the output is that goes with that particular input. So after we evaluate the function, that's the term we use, evaluating the function, plugging in a particular input, getting the output, f of x as a whole represents the function value, otherwise known as the y value, or the output, corresponding to the given x value or input. So one thing I want you to keep in mind as we use function notation is that anytime you see that notation f of x, it means the exact same thing as y. They are completely interchangeable. F of x represents an output. The reason this particular notation is valuable, potentially over just a y, is the fact that by having f of x, we can show what our particular input is. So it's a way of recording the input so that once we have a matching output, we know specifically what two numbers we're relating together. So the big thing to keep in mind when we're using function notation to evaluate a situation, to match an input and output, is we have to take into account order of operations. So typically a problem like this usually involves plugging in a number, combining using some algebraic operations, and then simplifying things down. Anytime we have to simplify something algebraic, we have to be very careful to consider order of operations. So as we start to evaluate functions, I want you to keep order of operations in the back of your mind. Keep considering the order you have to apply operations in order to make sure you get the correct output. So let's try a few examples where we use function notation. So we've been given a function which we're calling g of x. Notice this has a new name. We're calling it g instead of f. Typically use f, g, h pretty much interchangeably for the specific given values of x. So we want to first find g of 2 and g of -1. So what does this mean? Well, as soon as I see the g, I know that I'm referencing this particular rule that we called g. So g of 2 means I'm using the rule for g, applying it to the specific input 2. So g of 2 means take the rule for g and apply that rule, apply all its algebraic operations to the specific input 2. So wherever I have an x on the right-hand side in the rule for g, I'm going to put a 2 in place. 2 is the specific input I want to find an output for. So once I plug it in, notice I use parentheses to plug everything in. That's to make sure that I follow order of operations carefully. Then I'm following order of operations. So please excuse my dear Aunt Sally. So parentheses. Is there anything inside the parentheses that we can simplify? If there's not, then we move on. So next step is exponents. We do have an exponent in this problem, so that's the first thing we simplify. So 2 squared, notice we're just squaring the 2. 2 squared is the first thing we simplify. So we have 3 times 4 plus 2 times 2. So we've gone through parentheses, exponents. Then left to right, we look for multiplication and division. In this case, there's 2 multiplications, so we now have 12 plus 4. Last but not least, we have an addition, so our final answer is 16. So that means for an input of 2 into the function g, our matching output is 16. So if we were to write this as an ordered pair, this would be the ordered pair 2, 16. So let's try this for g of -1. Same kind of situation. We're using the same rule, now applied to a specific input of -1. So this means for every spot in the rule where there's an x, I'm going to put the specific input -1. Order of operations is followed the exact same way as before. So we know there wasn't anything to simplify in parentheses. I go to my exponent next. So -1 squared, anytime I square a negative, it becomes positive. So that becomes 3 times 1, and then plus 2 times -1. 2 multiplications, so 3, and then a -2 followed. So we can write that plus -2 as a -2 if we want. You can write it as plus -2 if you want. Either one means the same thing. Finally, we have 3 minus 2, so that's going to give us 1. So the output matching up to an input of -1 is +1. So this would correspond to the ordered pair -1, 1. Let's try a couple more, same rule, just different inputs. So let's give ourselves some exotic looking inputs. So we have g of a and g of x plus h. So what does g of a mean? Well, a is not a specific number, it's another variable, but we treat it the exact same way. So anywhere we had the generic input of x in our rule, we're now going to put in the specific input of a. So g of a becomes 3 times a squared plus 2 times a. Well, in absence of any other information about a, there's really nothing I can do here except just simplify and clean it up. So this becomes 3a squared plus 2a. There's nothing else I can do, so I leave it as that. That's my answer. What about g of x plus h? So now I'm taking the rule for g, plugging in x plus h in place of that generic input x. So here we have to be really, really careful about using parentheses, particularly for that exponent. So because I'm squaring the entire input, I'm squaring x plus h, so I have to put parentheses around the entire input that I'm squaring. Same thing for the 2 times x, which now becomes 2 times x plus h. The 2 has to be multiplied by both parts. So order of operations, we do our exponent first. Word of advice, this is not x squared plus h squared. When you square something that has addition or subtraction combined in between, you treat it as binomial multiplication. So that x plus h squared is actually an x plus h times another x plus h. In other words, it's a FOIL problem. We have 4 multiplications, not just 2 multiplications. So if you multiply x plus h times itself, you get x squared. You get 2 xh's, and then you have an h squared at the end. So make sure you're really careful about that. If you need to pause the video and make sure you can distribute that correctly, please do that. So once we've used the exponent, we have our multiplication. In this case, we have 2 distributions. So the 3 distributes to the first set of parentheses, and the 2 distributes to the second set of parentheses. So we have 3x squared plus 6xh plus 3h squared, that's our first distribution, plus 2x plus 2h. Now, one thing to keep in mind, particularly for the second distribution, is that if there were a negative in front of the 2, we would be distributing a negative 2. So just make sure you're really careful and methodical with your signs. Make sure you don't brush anything under the rug there. At this point, now we just look for like terms. So we have x's, we have h's, we have exponents. Anything with the same combination of variables with the same exponents can be combined into a single term. Here we don't have anything that looks like it can be combined, so that is our final answer. We have x's and h's, we have x squareds and h squareds, we have an x and an h together in one term. Each term is unique, so that is our final answer. So the takeaway from these two is that x can be replaced by any variable or any algebraic expression, not just constant numbers, and nothing really changes. We treat the problem the same way. We simplify it as far as we can. We just usually can't simplify it as far as we can when we have a constant number that we're plugging in. Although function notation is typically used with a function written in equation form, we can also use it when we're talking about ordered pairs or a graph. So the idea of relating the input and output in a strategic way can be done regardless of how the function is written. So one thing to keep in mind is that f of x and y are interchangeable, as we mentioned before. So anytime we have f of some number, that means we're looking for a y value or a y coordinate. So particularly when we're talking about ordered pairs or a graph, anytime we have f of a number and maybe we don't have a rule to directly find the output from the input, what we're looking for is a y coordinate. So based on the x value we're given in parentheses, we're looking for the matching y value, either determined from the ordered pairs or from the graph. So let's look at an example. Here we have a function that's given as a set of ordered pairs, and we want to find some particular function values. So first thing we want to do is find f of 2. So if you think of this as a question, what is this asking me to find? It's saying when x equals 2 in this particular function, what is y? What's the y value that goes with it? So I go to my function, again given as ordered pairs. I find the ordered pair where x is 2. Well, in my second ordered pair, I have 2, 5. So when x is 2, f of 2, in other words, the y value that goes with 2, is 5. So f of 2 is 5. Now let's flip it. So we want to find the x value or x values for which f of x equals 5. In other words, when y is 5, what is x? So now we're going in the opposite direction. If we know what the output is, what is the input that gave us that particular output? So I do the same thing. I go to my ordered pairs, but now I'm looking for situations where y is 5 as opposed to when x is 5. So I actually have 2 ordered pairs where y is 5. My second and third ordered pairs have a y coordinate of 5. So when y is 5, it's possible that x is 2, or maybe x could be 3. So both are actually x values that solve this problem. X could be 2, or x could be 3. So both are considered solutions to this particular problem. Now let's look at it in terms of a graph. So here's our graph, not a very pretty graph. But let's see if we can use this to find some function values. We're calling this function g, so now we're going to find g of specific values. So first thing we want to find is g of -3. So if we think of this as a question, we're saying when x is -3, what is y? So I go to my graph, go to the x-axis, find -3 on the x-axis. And then we're looking for the point on the graph that has an x-coordinate of -3. So it's actually just been shaded in for you. That's the point that has an x-coordinate of -3. So now we determine what is the y-coordinate that went with that. In other words, when the input is -3, what is the output that goes with it? Well, in this case, it just so happens the output is also -3. So g of -3 is -3 because we have the point -3, -3 on our graph. Let's try another one. So now we want to find g of 0. So when x is 0, what is y? So I go to my graph, find x equals 0 on the x-axis. Well, it's right there at the origin. And then I want to find the point on the graph that has an x-coordinate of 0. So it's just been shaded in. It's actually above this time. So when x is 0, what is the y-coordinate that goes with it? Well, in this case, the y-coordinate is 2. So g of 0 equals 2. Okay, so now let's flip it. We've got the same graph, but now let's find particular x values given a particular y value. So first we want to find the x values for which g of x is equal to 1. So same graph. Now we're going to flip it though. So as opposed to looking at the x-axis, finding a given x value and matching it to a point on the graph, now we've been given a y value. So we're being asked when y is 1, what is x? So as opposed to sliding on the x-axis, now I want to go to the y-axis and I want to find the point on the y-axis where y is equal to 1. So starting from the origin, that's 1 unit up, that's where y equals 1. Now I want to trace it onto the graph horizontally in this case to see where we have x coordinates on the graph with a y coordinate of 1. So it looks like we definitely have 1, maybe 2. So over to the right, we've got the point 2, 1. So it is a point that has a y coordinate of 1. So x equals 2 is one of the x values for which g of x is equal to 1. Now what about the point on the left? I've got a question mark there. Is that another point where y is 1? Well, it's kind of a point, but kind of not. Notice it's drawn as an open circle. So if it's an open circle, it's considered to be an endpoint, but there's not actually a point there. So notice right at that point, our graph jumps down below the x-axis. So that hole is there to indicate that we can get really, really close to that point, and as soon as we get there, we have a jump. We have a break in the graph. So even though it looks like y equals 1 at that particular spot, there isn't actually a point there. So we don't include that x equals -1, the matching x coordinate at that spot, as part of our solution to this particular question. So x equals 2 is the only solution for which g of x is equal to 1. Let's try another one. So now we want to find the x values for which g of x is equal to -1. So in other words, when y is -1, what is x? So again, go to the y-axis. I'm looking for the particular y value of -1. So starting from the origin, I drop down 1 unit. That's where y is -1. So now I want to trace horizontally to find the particular points on the graph that correspond to y equals -1. So I've only got one point here. If I trace over to the left, then I've got a point where y is equal to -1. So the x-coordinate that goes with that point, in other words, the input for the function that has a matching output of -1, in this case is x equals -1. So we've only got 1 here. Finally, one thing that function notation is helpful for is finding/defining intercepts on a graph. So we're going to spend a lot of time graphing in this class. X and Y intercepts are considered key parts of any graph. So we can use function notation to reference intercepts. So function notation is useful when finding the x-intercepts and y-intercepts of a function, which aid in graphing. So any x-intercept is of the form x, 0. So we can have any value we want for x, but the y value has to be 0. So translated into function notation, remember y and f of x are interchangeable. So if we set f of x to be equal to 0, in other words, if we assume y is 0 and then solve for x, what we're doing is finding an x-intercept. We're finding a point where if we were to graph the function, this would be the particular value where we cross the x-axis. So any y-intercept is going to be of the form 0, y. So y can vary, but the x-coordinate has to be 0. So to find a y-intercept, we assume that x is 0 and then solve for the matching output. Well, assuming x is 0 in terms of function notation is the same thing as evaluating f of 0. So by solving f of x is equal to 0, we're solving for x-intercepts by assuming that y, or the output, or f of x, they all mean the same thing, assuming that each of those is 0. And then for our y-intercept, we're assuming x is 0, we're evaluating f of 0. So let's do a couple examples of that. So we've been given a function and we want to find the x and y intercepts. So our first function is f of x is equal to x squared minus 9. So I want to find the x-intercepts and the y-intercept. Notice I write x-intercepts and y-intercept. There can be as many x-intercepts as you want. However, if we truly have a function, there can be a maximum of one y-intercept. If we cross the y-axis more than once, then if you visualize what that might look like, that means we have 2 points where we could draw a vertical line that would cross through both. In that case, we don't actually have a function. So for any function, we're only going to have one y-intercept. So for my x-intercepts, I'm going to set f of x to be equal to 0. In other words, we assume if y is equal to 0, what does x have to be? Well, f of x equals to 0 means the same thing as x squared minus 9 is equal to 0. F of x and x squared minus 9 mean the same thing. They're interchangeable. So I can factor here, or I can just move the 9 over. So let's just move the 9 over. So we have x squared is equal to 9. So I want to take the square root of both sides to get rid of the x squared, but remember, when I take a square root in an equation, I have to add on that plus minus to indicate that there are two different values that we could square to make this a true statement. So in this case, x is equal to plus or minus 3, because 3 is the square root of 9. So we actually have two x-intercepts in this case, 3, 0, and negative 3, 0. Now what about the y-intercept? So for the y-intercept, we assume x has to be 0, and we find the corresponding output, the corresponding y that goes with an input of 0. So that means evaluating f of 0. In this case, that means we're just plugging in 0 in place of x. There's only one x to plug into. So 0 squared minus 9 represents our particular output for this particular input. So simplify that down and we get negative 9. So our y-intercept is 0, negative 9. Let's try another one. So now we have a function that has a square root in it. So g of x is equal to negative square root of x plus 3. So for our x-intercepts, we assume g of x is equal to 0. In other words, assume y is 0 and solve for x. So that means the same thing as negative square root of x plus 3 is equal to 0. So I want to get x by itself. X is under the square root. So first thing I want to do is move the 3 over, or I could just add the square root of x to both sides and then everything will be positive. Either way, you're going to get the same thing. So square root of x is equal to 3 is what you should get down to. Now instead of getting rid of a square, we want to get rid of a square root. Both of those are what we call inverse operations. They cancel each other out. So if we want to get rid of a square root, now we're going to square both sides. So square both sides, we get x is equal to 9. So we have a single x-intercept of 9, 0. Now let's do the y-intercept. So we're evaluating g of 0. Let x be 0, figure out what y has to be. So plug in 0 in place of x. Square root of 0 is just 0. Negative 0 is still just 0. So simplified by adding on to the 3, we get y equals 3. So g of 0 equals 3, which means our y-intercept is 0, 3. So to summarize, a function is a relation in which every x is matched to only one y. In other words, for anything we input into the relation, we know exactly what our output is going to be without supplying any additional information. Every input is matched to exactly one output. The set of all inputs, or all x values, is called the domain, and the set of all y values is called the range. Function notation, f of x, g of x, h of x, anything like that, is just a shorthand for representing and finding x, y pairs. So f of x represents the output, it represents y for a particular input that we're calling x. So we can use this with equations, we can use it with ordered pairs, we can use it with graphs. Any particular representation of a function notation can be used and is used. So it can be given by a rule set of ordered pairs or a graph. And then say we want to find our intercepts, which is one component of graphing, which we're going to spend a lot of time doing. That's very helpful. To find, we solve for f of x equals 0, solve for x, and then find f of 0, respectively. Those give our x and our y intercepts.